times it's more around.
Right, why don't you make for 20 and 30, and then if companies want to do more, they can kind of, you can give a chance to do that, or like, but just figure out like how many events you think a year, or like a semester, then roughly what the cost would be.
Sure.
I might be able to make this happen.
Okay.
It may not happen until like next fall.
That's fine.
But I mean, if this is the thing we would need to do to really make this consistently great there.
Sure. Okay.
Yeah.
Cool. Yeah.
Okay.
I'll do that this week.
Okay.
Okay.
Great.
Cool. Thanks, John.
Yep. So let's get started. So by judging by the number of people here, it looks like homework 3 was a doozy. So the good news is you guys have completed like 2/3 of all the kind of homework assignments. Essentially, there are going to be 3 other homework assignments, but the frequent item one and the graph ones are like half homework assignments, right? So they're only worth 50 points as opposed to 100 points. The regression one is worth 100 points. I think it's also going to be. I've heard that if I make it like I've done the years past, it'll be much lighter than the last couple of homeworks as well. So it's good that if you're here, I'm guessing it probably means you finished. You finished homework 3, so it's so hopefully it's good that one's over with. So did people have fun with the medians question, or was it kind of like, I've had so much else to do? Okay. Yeah, so it's a busy time this semester. So, so let's see. So the frequent one, I'll try and get this assignment up soon. It should probably, I think it'll take you like easily less than half the time of the clustering assignment. It'll be due before spring break. Also. Next week a week from now is going to be the midterm test. I usually have this like on the day right before spring break, but spring break is like a week later this so this semester than it usually is. So we're going to have it next week. This is an old version. So it's going to be fair game to cover anything that, I'll say, let's not worry about the lecture on Monday. Anything up through the lecture today is fair game to be on, is going to be fair game to be on the midterm. I'm going to allow, on the midterm, I'm going to allow one sheet of paper. You can use both sides of that sheet of paper as notes. Okay, to bring into the midterm. And so it's I've gotten lots of advice and I've read that you as students kind of retain, you learn the material better if I have like tests in the class. The same point, you know, I think this is a much more kind of applied area. I'd rather you do something, you'd be able to write code and see it. I think that's also more important. So this is, it's midterm test, it's worth only 5% of your grade. Okay, so, you know, you saw it in there, so it was in the syllabus. It's not a huge amount of your grade, but it will, you know, it's still going to be in class next, next Wednesday. And so, you know, I don't mean to make it too hard either. If you're generally following along with what you're doing, you're understanding, doing well in the homeworks, you should be able to do pretty well on the test, I expect. Okay, so a lot of you are doing very well on the homeworks I've been seeing, so hopefully you should do well on this, yeah.
Will the topic on ethics in the paper be covered in the midterm as well? Is that fair game?
So yeah, so I mean, I can ask you about it,
Okay.
right? Now, I'm not going to expect you to be able to reproduce what's in the paper, right? You know, I'm going to ask you things that I expect you should be able to know without looking at notes, but I'll allow you to bring in one page with both sides for notes on there. So it's stuff you should be able to answer all within the class period. I don't think it'll be something you'll be rushing to finish, right? But I could ask you about, you know, like, I could ask you some question about it. You know, I'm not saying I will or I won't, but it's fair game. Yeah.
Are you planning to upload some sample paper, sample midterm for?
I was not planning on doing that. So think of this more like a quiz than a test.
So it would be full of like multiple choice questions or short answer type questions?
Yeah, so it should be short answer type questions. In the past I've made it so you had 3 pages, so front, back, and front again, and you only wrote on those pages, right? You maybe not multiple choice, but kind of a short answer, or I think I've had something like a multiple choice in the past. Say which of these is valid for this approach or something like that. Yeah.
Will it potentially be proof heavy? So like,
I'm not going to ask you to, I don't think I'm going to ask you to prove anything. Yeah. Yeah, so I don't, yeah, it's not going to be like an algorithms test. It'll be more, did you know, I want to kind of check that you're understanding kind of the concepts that we're covering in this course. Right. So, okay, so I'll say a bit more about it. I'll say a bit more about it on Monday again. So if you have questions between now and then, I'll try and you know, you can ask them again next week, Monday in class. So today we actually have a lot of material I'm hoping to cover. So we're going to talk about so kind of the whole topic of dealing with high dimensional data and like so dimensionality so reduction. So if kind of where you have a lot of data, meaning you have data, say, with lots of different attributes, you want to find the ones which are the most meaningful somehow. And so I'm gonna, what this is gonna go through is basically, we're gonna talk about one core tool, how to use this today, and we'll talk about a couple other kind of related things in coming lectures, but we're gonna look at these, at the singular value decomposition as a tool for doing dimensional reduction. And so the goal is going to be to kind of explain what is the singular value decomposition doing and how do you do this. And this is going to cover lots of ground. So, so who's taken a linear algebra course before? And who's heard of the singular value decomposition? And so who's never heard the singular value decomposition before? Okay, so this will be kind of, for those of you who haven't seen it before, this will be kind of a very fast kind of introduction to this. So there's more notes online. You may need to read up about it, but hopefully everything you need to know will be covered today. I'm going to go through a lot of stuff. Okay, so the data, the input that we're going to be analyzing, we're going to think of as a matrix, and I'll say the matrix is in Rn times D, and so that means I'm going to think of it as a matrix where I have n rows and D, so D columns, and then within this you'll think of one of the data points as being AI. It's a row in here. So AI is going to be in our D. So it's going to be a D-dimensional vector. And so I'm going to think of both N and D in large, and basically what I'm going to do is essentially we're going to talk about mapping this into, let's say, we'll call this AK, which, actually, let's not use AK. We're going to map this into a subspace F, which is going to be is only going to be K dimensions, where K is going to be less than D, but this K-dimensional space is going to capture most of what's going on in the data A. Okay, so you can think of D being something like N being hundreds, D being 10 or 100, and K being like 2, right? So I can map it down to a two-dimensional space, where then I can, if I have high-dimensional data, now I can plot it if it's in 2 dimensions. I can kind of see what's going on. How do I choose 2 dimensions where I would plot this data, for instance? Okay. Before I get into kind of more mathematical way how to think about this, I really want to specify that in order for this to make sense, I need to think about the units here. So the units on all of the columns should match. Okay, so if you remember that picture I showed you on a slide earlier where it had this road sign, and it said the miles above sea level, the year the city was established, and the population, added these up. You're doing the same thing if you're running the SVD on data where the units on the columns don't match, right? So you're thinking of these as a bunch of data points, and there's D attributes. But if they're measuring different things, then you're going to be kind of twisting them and doing something like Euclidean distance on them, and it's not going to make sense if these don't match. We'll talk about something next week, Monday, in metric learning. I've finally put up lecture notes on this about ways to deal with when the units don't match and how to kind of learn a good metric on the space. But in order to apply this, you really should do it so all the units match. And so there could be just let me mention a few examples of this. So like you could say that each row is equal to a point in time, and each column would correspond to like the temp at some like weather station, right? So I'm measuring every hour. I have 40,000 weather stations across the country. They each tell me a reported temperature every hour, right? So they're all reporting temperature, so it's all in Fahrenheit, right? Or all in Celsius. It doesn't matter which one, but I convert them all into the same unit. Another common thing would be thinking of a time series, say of the price of a stock. Okay, so every point in time, I'm going to have price 1, price 2, price 3, up to price uppercase T, right? And so I'm going to convert this into a matrix using a trick that looks like the shingling over text. what I'm going to do is I'm going to take every, say, 3 data points, and this is going to be row 1. Row 2 is going to be an overlapping set of 3 data points. Right? Each is a stock price, but I've turned it into a matrix in this way. And so this is a common way to model and understand properties over some time window in time series. I'm going to take each of these kind of set of D elements in a row, and then I create a set of D-dimensional vectors. And if I P of them, then I have n minus D distinct rows in the matrix. It's also common, instead of just for stocks, what's more common is actually to take the difference between every 2 of these. So go and look at Q1, Q2, where Qi is going to be, say, Pi minus Pi plus 1. And then do the same thing with windows over these guys. This helps to understand the change over time. Or maybe I normalize this somehow by the total price. And so these are very common things in dealing with time series. But then you put them in this matrix form, and often you first simplify them by doing like dimensional reduction. I may take a huge number, kind of a sequence of, maybe I get this every second, and I want to look at the differences, or I get it every day, and I want to take like a month, so 30 days worth of thing, but I think the phenomena can be described in only 2 or 3 dimensions. This is a common thing to happen. Okay, but if you don't assume all the units match, some weird things can happen because you're mixing and matching these units, and so just keep that in mind. Okay. Okay, so we're going to think before we, okay, so now we're going to think abstractly about this, now about this data. And the idea is we're going to have a, let's say a data point, and I'll call this AI. Think of this as one of the rows. This is in RD. And the goal is going to be to map this, so map to a subspace F. And this will be, this subspace F will only be k dimensions. How do I map a high dimensional data point, I can't even draw it, it's too high dimensional, onto a k-dimensional subspace? And the key thing to understand is how to map this onto a one-dimensional subspace. Okay, and then we're going to do this we're going to do this k times, essentially. And so the key to this, to understanding this, is the dot product. Okay, so I'm going to start with a unit vector, u. Okay, so that means u is going to be in RD, and the norm of the L2 norm of u is going to be 1. And so I can think of this as there's some origin. It makes sense to think of the origin even high dimensions, and u is going to be some vector. And I can think of kind of the one-dimensional subspace which passes through this vector u through the origin. Okay. And then if I draw my data point, AI, I want to project it onto here. I want to map it to the closest point onto this subspace here. Okay, and it turns out there's a nice mathematical way to do that. It turns out that this location here, I can write this as u, right? It's on this vector, so I need to scale this vector times the dot product between AI and u. Okay, this dot product is a scalar, and the scalar is exactly this length here, right? So this length is exactly AI dot product u. Is exactly this length here, and so I've taken this unit vector and I've scaled it up to here. Okay, so this is the geometric view of dot products. Yeah.
You have the direction of u, right?
Yeah, so I'm given u. We're going to talk about finding the best u, Eventually we're going to get to that. And and the SVD is going to do that for us. Okay, we're not going to, in this course, I'm not going to tell you how to find it, other than you're going to call the SVD inside of whichever programming language you want. Yeah. Okay, so you're given this direction U, you want to project A onto this subspace. I just do this. Okay, this gives me this point, this gives me this distance here. Okay, I can also think of doing multiple points, right? I can also think of having, I can have A2, I can have A3, or A1, A2, A3, and so forth, and each of them ends up being projected onto the subspace in the same way. And so I can think of this as now giving a sorted order over these points. I've somehow, in one dimension, I can sort them, right? I have one coordinate which describes these points now. This was similar, really, it's going to be the same thing kind of like we did with spectral clustering with the the first Eigen vector here. It's essentially doing the same thing, but we're gonna be able to understand exactly kind of how we choose these directions U and what they're optimizing. It'll be more clear in this setting. Okay. Yeah.
You wrote in red the U, U. Is that U times that, or is that going to be the dot product?
So this is a vector, and this is a scalar, right? So it's a vector times a scalar. Sometimes people write x to multiply b times. Sometimes they put a little dot. The dot is confusing because sometimes people write the dot product with the dot. I'm just going to put things next to each other if I'm multiplying them. That's the standard way it's written because I guess that has the least confusion associated with it. For dot product, I'll write it like this inner product. I think this is the least confusing way in order to do it. Okay, so this is, if I have one dimensional subspace, I can find the unit vector, which is kind of going through it, and this is how I project onto this one-dimensional subspace. If I want to do a k-dimensional subspace, right? So page here. So if I have a k-dimensional subspace F, what I'm going to do is I'm going to define now a set of these vectors, U1, U2, up to UK. And so I'm going to say that these are a, let's say, an orthogonal basis if each UI is going to be a unit vector, and also UI dot product Uj for I is going to be exactly equal to 0 if I is not equal to j. So this means that they're orthogonal to each other. The dot product equal to 0 implies that they form a right angle in high-dimensional space. Okay, the really nice thing about thinking about this, we're in d-dimensional space, but I've drawn this a picture, right? It turns out this is totally okay. These two define a two-dimensional space, so it makes perfect sense to draw them in the two-dimensional plane. There's no illusion going on here. There's nothing funny about high dimensions. This allows me to get down to 2 dimensions here. Okay, it exactly defines two-dimensional space, and if I have k of these, it's exactly defining a k-dimensional space. If you think of the coordinate axes, defining the coordinates of a value, you think of the x, y, and z direction. Because these are orthogonal and unit vectors, they're going to define a k-dimensional space that's a subset of a high-dimensional space the same way. Okay, so it's just like thinking about coordinate axes, but they don't necessarily need to be aligned with the x, y, and z coordinates. Okay, and so now I can So one property I'm going to have is that for all, let's say I have X in this this k-dimensional subspace of RD. So F is going to be a subset of RD, but it's a k-dimensional space, right? So it will only take, say, 2 dimensions out of 100. It's a linear 2-dimensional space. It turns out I can always write, you can always write, if these vectors kind of span this are sufficient to describe this k-dimensional space, then I can write X as the sum of I equals 1 to k of alpha I times ui. Okay, these ui vectors are d-dimensional vectors. Okay, so each ui is in RD. So I'm taking d-dimensional vectors and I'm adding up k of them scaled by something. This is a scalar. So, and alpha I turns out to be exactly x dot ui. So this is a scalar. So I'm taking these k vectors in space and I'm scaling each of them and I'm adding them up. And you could think of it as like walking on this k-dimensional kind of the space, like say there are these streets that go on essentially north and south. I think I've got some streets on some twisted angle that are going in k dimensions, and I'm walking on each of those some distance. It doesn't matter which ones I do first, but I walk in each of those directions some distance, and I can represent any point in this k-dimensional space. Okay. Yep.
So X is a k-dimensional point? Or
Well, it's a d-dimensional point,
Oh,
but it lives in a k-dimensional subspace. So it still has, it's still a dimensional vector. So it has d coordinates and stuff. Now, one of the cool things is I can give it k, because it lives in F, which is a k-dimensional space, I can give it k dimensions which describe it, given that it's in F. Right? So I can give k coordinates which define it, and these coordinates are going to be essentially, I can define this as alpha 1, alpha 2, up to alpha k. So it is x dot u1, x dot u2, x dot uk. Right, so this is now, this was a d-dimensional vector, this is now a k-dimensional vector. Right, if this is like a 3-dimensional space I'm defining coordinates in, that's not sufficient to describe in a 10-dimensional space. I can only describe those in the 3-dimensional subspace. Right, but I can now give them a new coordinate system. And within that space, I can say, okay, I only need k coordinates to describe where it is. I don't need the d coordinates anymore.
so the difference are 0, those coordinates that, d minus k, there are d minus k coordinates that are 0, and on that, sorry.
These are not the same. So x equals x1, x2, up to xd, right? So it's a d-dimensional vector, but it's a different coordinate space, right? It's like I took the original xyz coordinate space and I've twisted it into, say, 2 dimensions. This is maybe same way you can understand, right? And so it's not the first 2 coordinates of here. It's a different coordinate system, right?
Yeah.
Think I have some graph paper, right? Which and I kind of hold it on an angle, it gives me a coordinate system that lives in 3D. But I can only describe things which are on the graph paper, right? And that's what the just the same way that this gave me 1 coordinate here, right? I have this 2-dimensional space, but if it lives here, I can describe each point by just the 1 coordinate where it lives there. I'm ignoring the part that comes off of it. Okay, so this is cool. What we want to do though, okay, so this is kind of how to think about high dimensional geometry and linear subspaces. What we'd like to do now though, goal is on input some matrix in n by d matrix, so n data points in d dimension, and a scalar, or not just this, so this is some integer, and some integer k, say less than d. The goal is to find k-dimensional subspace F, which is going to be the arg-min of over all of such F, minimizing some sum of squared errors formulation between A and F, where I can write the sum of squared errors A F, so as the sum A, okay, of the difference between AI times the projection onto the subspace F squared. Okay, so what is this looking like here? I've got these data points. Each of these is AI. This is in RD, and I'm going to find a k-dimensional. This is F k-dimensional, and for each of these, I'm projecting them onto here. So this, for instance, if this is AJ, then this is the projection onto F of AJ is this point here. Right, so all of them I can think of their projection onto here, onto this this k-dimensional subspace F, and I want to minimize the sum of these squared costs of projection. Okay, so when I draw it like this, it looks a lot like this linear regression problem, but I'm doing this orthogonal projection here, right? This is the shortest projection, not in some chosen y coordinate that I'm minimizing here.
Do you choose K in a similar?
Yeah, you're going to have to do something like clustering. This is going to be, you assume it's given to you, but you can also, you'll have to try and figure out what is a good subspace to find, and you can plot this cost as a function of K and look for the elbow, is generally what you do. Yeah. Right, so I'm trying to do this, and now in the linear regression, I had a function, so for every value x, there was always a value here. Now I'm dropping dimensions, right? So it could be a line in a 100-dimensional space. It could be a plane in a 100-dimensional space, but it's kind of hard to think of 3 dimensions, 100 dimensions in a 100-dimensional space. A line in 10 dimensions gives you a good, or even 3 dimensions gives you a good idea. I can come at this line from multiple directions, so I can't kind of map, I can't do the inverse map. I'm losing some, even if I knew the cost of this residual, it could move out and make d minus k-dimensional null space here. That's missing. Okay, so I want to find the subspace F, which minimizes this cost. Right, and remember F was defined by these k orthogonal so unit vectors. Okay, and if I have those, I can do this projection by just projecting onto each one of them, and each one gives me a coordinate in the space, or I can recover by doing this thing where I'm adding this up, where this is the dot product and this is the unit vector I chose to define the subspace. Right? So this is how I would define the subspace with these orthogonal unit vectors. The goal is then to find the best subspace, which minimizes the sum of these squared errors. And again, it's sum of squared errors because the math would be convenient. There's this nice solution to it. Okay?
So we will have D choose K to be the size of F possibilities for F.
It's infinite. Okay, so it's I can think of the lines in 3D like all possible, line. Now, we'll start by restricting that the lines go through the origin, And then, but still there's like an infinite number of lines here. So I have been, yeah, so it's not just a subset of the original dimensions. I'm kind of making linear combinations of these dimensions. Right, so this is, it's kind of, if you just see this formulation without knowing anything about the math or SVD, you would think, okay, maybe this is impossible to solve. It's a really hard optimization problem. It turns out that this has been studied heavily for 50 years how to do it, and there are existing several ways to kind of any kind of programming language you have to call this what we call the singular value decomposition. Okay, so this problem, so as is stated up here, this is PCA, but there's about is if I also, you see that, I use that color, if you also force F to contain the origin, then you can solve this with the SVD. So we'll come back at the end of the lecture and say, I don't want to restrict that it goes through the origin. Then that's the general PCA problem, which is a little bit different. Once you understand the SVD problem, it turns out it's not hard to remove this restriction. It goes through the origin. But for now, we're going to assume that we're going to restrict F to go through the origin, to contain the origin. This will be simpler conception. Okay, so the key to this is what's called the singular value decomposition. Right? So a number of you have heard this before, but maybe you were not taught it unless you took my class last fall, to think of this as a way of doing dimensional reduction of data in the way I described. Okay, so the singular value decomposition is a way to take this matrix A and you're decomposing it into three much larger matrices. But they have special structure in them, and that special structure will allow us to recover these best subspace approximations that we're hoping to get. Okay, so let me explain what is SVD, and we'll go through a bit about how to think about it. So the SVD, so technically they're going to have two orthogonal matrices. U and V are going to be, so these two are going to be orthogonal, which essentially means that they don't carry any kind of length information. They're essentially doing a rotation of the space. U is going to be n by n, n by n, and this one's going to be d by d. So it'll be easier to think about V, or V transpose, in that it's kind of, you're taking your d-dimensional space and it's rotating everything in the space somehow. It can do mirror flips as well, but don't worry about those so much. There's only one mirror flip that matters, and it's just one bit. The S matrix is going to be, depending on your programming language, it might be d by d, it might be n by d. But to recover A as the product of these three, it needs to be n by d. And so in MATLAB, it will be n by d. In Python, unless you do some special version of it, it's going to be d by d, which means that it will just be the top part here. Okay, but the difference is everything here, everything in here is zeros. The only thing that's not zeros is going to be on this diagonal part. Okay, so the fact that n by d or d by d doesn't matter so much. I think it's annoying that Python doesn't do it this way, but that's okay. Okay, and so this is capturing all of the scaling information about the matrix. If I multiply a vector by this matrix and it's longer than it was before, that's because something in here had a big number. If it gets smaller than it was before, it's because something in here is a small number. Okay, so that's kind of at high level, that's what's going on. This is rotating the data you multiply it by. If I multiply something on the left, I'm doing AS. right? I'm multiplying, and x is a d-dimensional vector. We'll go through an example with this. V will rotate it, s will scale it, and then u will rotate it again. That's essentially what's going on. Yeah.
So all the vector, unit vector in U, and all the vector in U is orthogonal to each other,
Correct.
and
All the column vectors in U and the row vectors in V transpose.
Okay. Is there any relationship between the vector in U and vector in V?
There is a relationship in that they are part of the SVD of A. But we're not, these are n-dimensional, these are d-dimensional, so it's hard to compare them,
Oh, okay.
right? They're really, yeah. So let me, another picture here, which kind of breaks this down a little bit more. So the vectors in S are called these are called or the values in S, singular values. So each of the things along this diagonal are the singular values, and that tells me how much a particular dimension, right? So if this number is 2, I'm taking a vector in that space and I stretch it by a factor 2. Okay, the right singular vectors are in V here, right? So Vj, right, which here is the right singular vector, and then these are the left singular vectors in U. For data analysis, I'm not going to need to talk much about U. We'll think mainly about S and V here. And the right singular vector is basically going to, this is part of an orthogonal. These are all, these row vectors in V transpose are going to be orthogonal to each other. And the jth one corresponds, the right singular vector corresponds with the jth singular value. So how much I'm scaling something along the jth right is by the jth singular value. So these correspond with each other. So then there's a correspondence by the jth and the jth one fit together. It gives a one-dimensional subspace that makes up A in some way. And so these define a basis, right? This is an orthogonal matrix, so all the rows are orthogonal basis. I started with the d-dimensional space, and the original coordinate system was a d-dimensional basis, and this is a new one, right? So this rotation is giving me a new d-dimensional basis, is what's going on here. Okay, so let's go through an example, a very small example here. A question?
This might be a dumb question, but what is the maximum amount of singular values matrix can have? Because that's the factor that gets...
Yeah, so it can have the minimum of n and d. In this case, I've drawn one where n is bigger than d, so then it can have up to d non-zero singular values.
Okay.
Yeah, but if the rank of A is smaller, then it will have as many as the rank. The rest will be 0. And this will come out of some stuff we'll talk about in a couple minutes. Okay, so let's go through a really small example here, right? So this is A, this is going to be n equals 4, d equals 2. I've chosen this so that it happens to, the average of each column is 0. And that means that the subspace I'm going to want to find is going to go through the origin. It's just going to work out that way. And therefore, each row you can think of as a point in two dimensions. All right, and I called the SVD, say in Python or MATLAB, and it was MATLAB because I have zeros down here, but it's going to give me these output here, right? So S is mainly zeros except for the first singular value and the second singular value. Right, this is V. I think this must be V, not V transpose. So these columns should be orthogonal to each other. Same with the columns of U here. Okay, now they're just numbers. It's hard to look at the numbers. So let's kind of try and look at this from a picture of what's going on here, right? So I'm going to pick a vector x, and it happens to be, I've chosen x so that it's a unit vector. Remember, a unit vector means it lives on this circle, right? So it's on this circle. When I multiply x by v transpose, right, I'm going to look at what happens of a times x. This is going to be equivalent times u times s times v transpose times x. And so I'll look at this in 3 steps. The first is what happens when I do this. The second will be what happens when I do this. And then the third part is just going to be the same as multiplying just by a. And I can draw pictures for the first 2, so I'll do that. And so originally I have this, and these are unit vectors, so they point to someplace on the circle, and they are orthogonal to each other, right? So they are at a right angle with each other. And so when I multiply x by v transpose, what happens is, so v1, which was here, now becomes the x-axis. And v2 is now the y-axis. And so what happens here, I took x and I projected it to v1, and I'm going to get a coordinate which looks like about negative 0.8. Right? That's the distance from the origin along here. It's a negative value, and it turns out that the x-coordinate is about negative 0.8. Right? The y-coordinate is onto v2, and this is about 0.6. And if I project here onto the y-coordinate, it's about 0.6. Right, so I've gotten a new coordinate system now, and so this now I can write as in the new coordinate system negative 0.8, 0.6. If I chose these numbers correctly, it'd be a unit vector still. I have not changed the distance from the origin of xc.
Why do you project
That's what multiplying by the matrix V transpose does. Right? If I multiply by the matrix V transpose, I'm going to get a new point, xc, which is going to be roughly negative 0.8, comma 0.6, a two-dimensional vector.
Why would it be negative, though?
Because V1 was pointing in this direction here, so if I project onto the subspace, this is the positive direction, this is the negative one. That's determined by V1, remember, is the first column here, right? This is V1, and those coordinates are negative, right? Okay? So this is what multiplying by V transpose is doing. It's rotating the coordinate system. And I think it did a mirror flip here as well. Okay? Okay, so I've got this new point xc, and now I'm going to multiply by this S matrix. This S matrix, I didn't write it up here. Remember, it's like basically 8 and 2.3. So S was basically 8.1, 0, 0, 2.3, 0, 0, 0, 0. Okay, so I'm starting with a two-dimensional vector xc, right, which was about negative 0.8, 0.6, right, and I'm multiplying it by S, the first two coordinates. So it's going to output a four-dimensional vector. Let's draw the first 2 dimensions here. The first one is stretching along the first coordinate. It's taking the first coordinate of xc, and it's stretching it, right, by 8, right? So it was about negative 0.8, now it's about negative 6.5, something like that, right? So this will be about negative 6.5. And then the y-coordinate, which is 0.6 multiplied by 2.3, so what is that going to be? About 1.5, right? So the y-coordinate is about 1.5, right? So if I drew the unit vector here again, I'm well outside this unit vector. I've increased the size of all of this here. All right, and so I happen, any unit vector I started with x will lie on this ellipse someplace. It's stretched more along this dimension than it is this dimension. And the ellipse is defined by two axes and two scalar values, just like the axes v1 and v2. And there's correspondingly an ellipse that lives in the original two-dimensional space that x was defined. It's stretched this way and that way, right? So there's an ellipse that it corresponds with an ellipse that goes through here one direction and the v2 direction, right? So in order to define that properly, I kind of need to first rotate, and then I can scale along these axes, not the original coordinate axes. That give me an ellipse restricted to those coordinates. Okay. Now, in order to get back into whatever the right coordinate frame is, I need to multiply by u, right? So this is actually a four-dimensional point when I multiply by s, but the second two dimensions are zeros because it was all zeros here, right? So I think there are two more dimensions coming out of the screen, and those are both have a zero coordinate, so it really does lie in the plane here. I can't increase the dimensionality of the space that the points lie on by doing this. Okay. And so then the U matrix kind of moves it into a four-dimensional space in the right coordinate system there. So I'm taking the data in the original two dimensions, I'm rotating it, stretching it by the ellipse, and then I'm rotating it again into a four-dimensional coordinate system. That's what the SVD is kind of doing. Yeah?
After you multiply it by u,
After S, it's already in four dimensions.
but there's zeros.
They just happen to have zero coordinates. But now I'm free to take this four dimensions and do a rotation. Rotation does not change the dimension or the length. So I had to get into four dimensions before I can rotate into that space.
And also S can never be negative, right? There can't be any values there.
Correct. Yeah. The S's will never be negative. Yeah. Although the you can have some like if I could essentially change I could flip some signs between V and U and everything will work. So it's not unique up to signs everywhere. But you can imagine it going the other way and then the U kind of fixes it. So you could run it in two different ways of constructing SVD and get slightly different results that way. Also, if the singular values happen to be exactly the same, which is on noisy data should never happen, but they'll often be close, then you could switch the order of things in that way. Okay, so it's kind of an intuition of what's going on here. Okay, so now that we have this SVD tool, we can finally kind of solve this problem. How do we find how do we find the best subspace F, right? So I wanted to find this best k-dimensional subspace. Now, how do I find this, right? It's going to fall out of this. Right, so F is going to be defined by this set of these orthogonal vectors, U1, U2, up to UK. And it turns out these are so I have an input A, and that these are going to be the top K right of A. Right, so I'll do A, I'll call the SVD, and I'm looking at the right singular vectors. These are going to be V. Right, so this is often called VK, is going to be V1, V2, to VK. Each of VI, or VI, or VJ is going to be in RD. And this is a column vector. Okay, so by calling the SVD, it basically determines for me the best top K, the best K-dimensional subspace, which is going to minimize the sum of those squared, of those errors of those projections. If I want to look at any one direction, right, those vectors could come from many different directions. I want to say for any direction, I want the sum of those visual vectors to be directions that are described by this subspace here is going to be 0. So it turns out that the direction which gives me the most error of all the residual vectors is going to be vk plus 1. This is going to be the k plus 1 singular vector here. And so by choosing the top k, I'm also minimizing under this loss function. That's the difference between the sum of the squared errors is, well, actually, I'll write this. That'll be more clear next, right? Well, actually, I want to come back to what I was just saying, but I can say that the error x minus pi of f of x squared, right? I'm summing this over all of the rows of A. This is going to be equal to, because x and v are going to be these, this is x vi, so both of these are d-dimensional vectors. Okay, so I can write, because v, the full v-dimensional space, d vectors here gives me a basis, I can write x in terms of this basis like this, and a space here. Right, so these are both d-dimensional vectors. This is exactly x, and this is exactly x projected onto f. Right, and so this is going to be equal to I k plus 1 up to d of x vi squared. So the first k cancel, and then I'm just left with which ones are here. It turns out each of these is a scalar times a unit vector, so I can just look at these square terms there. And so this is how much error I'm going to have here, exactly this. And it turns out that this is equivalent, that the sum over all ai in A, x minus ai minus pi of x. Let me write this more clearly. AI minus AI squared. This one is going to be equal to sum over I AI in A, sum over J equals K plus 1 to D of AI Vj squared. Okay, and it turns out that this is going to be equivalent to J equals K plus 1 to D times these singular values squared. Right, this is where this S matrix is going to be sigma 1, sigma 2, up to sigma D. Right, so these are the squared singular values. So the sum of the squared errors of A, it turns out this expression is going to be equal to the sum of the singular values. If I just look at the J term here inside of this sum, right, is just going to be the sum of it's just going to be the squared jth singular value here. So the singular values are capturing how much air is in each of these directions. Right, so that's why the subspace is that I'm choosing is the top K, because that one has the most kind of, when I project onto that direction, there's the most variance of the data in that direction. And I'm sorting these dimensions, forcing that they're all orthogonal to each other of decreasing variance. So I'm always choosing the direction which has the next most variance that's orthogonal to the ones I've already found. Yeah.
Okay, so is that something that occurs naturally that comes out of the SVD?
That comes out of the SVD.
I would have thought you would have taken like the rows in the V matrix that correspond with the smallest singular values to indicate like less variance or the opposite of that.
Yeah, so the rows think of data points, the columns think of original coordinates, original attributes. So the rows are, you can think of, you could think of selecting a data point that has that's kind of very far from the average, and that would cause a lot of variance. This turns out to be interesting for other things. This is the plus algorithm or the Gonzalez algorithm, and that you're picking the most extreme point because that affects the cost measure. But I'm not restricting to data points here. I'm thinking I'm working with the dimensions, and I'm saying that I want to find some low-dimensional representation of attributes I have. I've collected stock prices for 30-day windows, and I'm saying there's some two-dimensional space that tells me what type of 30-day window this is. Right? There's only two dimensions that need to describe the patterns going on here. There's a weather system, and there are really only three parameters that is at high temperature in the East Coast and low on the West Coast, or vice versa, or high north-south. Maybe that's how it breaks down. So I'm kind of mapping to a two-dimensional space that captures most of the information. But this space is not so interpretable. It kind of, sometimes there's some nice interpretation, sometimes not. But it's easier to work with, I can draw it, and these are kind of the advantages I get. Okay. So the SVD kind of captures a lot of this information. There's one more thing that falls directly out of this. Yeah, I'll just go here. And we can find what's called the best rank K approximation of A. So before, I'm mapping to this K-dimensional space, but I can think of it also as I want on matrix AK to approximate A, but I want to enforce that the rank of A is at most K. And I'll always use exactly K, right? Rank of exactly K. So people have heard of the rank of a matrix from linear algebra class. Turns out rank is equivalent to the number of non-zero so singular values. It has to do with the dimensionality of the subspace I need to capture all of the data. So basically, in order to find the best rank K approximation, so I'm forcing that this is still a d-dimensional matrix, right? It's an n by d matrix that looks like AK. So do something like A minus AK. I can subtract two matrices. They're the same dimensions, right? And I can then take the norm of this, and either the Frobenius, right? The Frobenius norm is exactly going to be the same air measure as we're looking at here. This is exactly going to be the Frobenius measure, the Frobenius norm of A, and if this is essentially going to represent A minus AK. This term is essentially going to represent A sub K, right? So I can recreate this. This is also going to be, right, so this is going to be is an n by d matrix, but all of the data happens to lie in a low dimensional subspace. And so all I basically do is I can turn all of these except for sigma 1 up to sigma k, I'm going to keep, and then the rest I'm going to set to 0, the singular values. Then I can multiply back through by vk, or just v transpose, the same matrix, this modified singular value matrix and the same U matrix, and I'm going to get the best rank K subspace by saying these to be 0. The way to think about that is because this is all 0, then there's this big part of this matrix which I keep it so it's orthogonal, but it doesn't really matter because it's being multiplied by zeros here. These are all zeros, so this is, you know, what's the right way to write this with, like, one of these guys, how do you draw that? You know, so it doesn't matter what's going on in there because it's being multiplied by zeros, right? So the same thing when I set those equal to zeros, then I'm going to get the same phenomena here. This becomes all zeros, so now this part of this matrix and this part of this matrix are also, you know, this kind of symbol here, right? I don't really care what's going on there. So it means that I can actually represent it by kind of k n-dimensional vectors, k scalar values, and k d-dimensional vectors. And this actually starts to become a more compact representation than an n by d matrix. You can often have that n times k plus k times d is going to be much less times d. This is the number of coordinates in the original A, and this is in this compressed representation after I've gotten rid of the stuff that I don't care about. Okay, but it's going to still be a d-dimensional matrix, but I can represent it in a smaller form. And it's kind of by compressing it down to a lower dimensional subspace that still lives in RD, but maybe I've gotten rid of some noise. That's kind of what you are hoping is going on here. I could also then, I could work with the new coordinate system, the k-dimensional coordinate system, and then maybe algorithms are more efficient, right? Because every time I touch a vector, I may need to read d coordinates. Maybe k is much less than that, right? So these are the sort of advantages that you can get out of here. Either you're reducing noise, or you're making algorithms run faster, or it's just kind of some simpler representation here. Maybe more interpretable just because it's lower dimension. Although the coordinates don't move so much anymore. Okay, so this was how to do dimensionality reduction and using the SVD. It's kind of a whirlwind tour of it. I want to mention two additional extensions here, and then I'll mention one more. I'll mention multidimensional scaling, which will also use this, and some other metric learning stuff in the lecture on Monday. And then after the midterm, I think, but before break, I'll talk about some ways of doing this that might be more interpretable, something like selecting columns, or might be more scalable, or something you can do like in a streaming setting. So we'll talk about some other variants of how to scale this up and some of those implications next week. Okay, but the first is going to be PCA, and then which I alluded to earlier. And the second is going to be Eigen Values and Eigen Vectors and how these are related. And you'll see they're basically the same structural thing. You just need to do a little bit. Okay, so PCA is to find k dimensional f, which so minimizes again a minus the projection of f onto A. And so when I write this with the matrix and the projection, I'm projecting every single row. That's essentially the right way to think about it. Right, so I want to minimize this, equivalent to AI minus projection of F squared, but there's no restriction on the origin in F. Okay, so the right picture to have in your head when thinking is you have some coordinate system, and then your data lives kind of like this. Right, so the right subspace So SVD for a one-dimensional approximation might give you this subspace, the red one here, which doesn't really go through the data at all. But if I do PCA, I can do this. It's going to go through the data, but it does not go through the origin. Okay, so if I'm going down to 2 or 3 dimensions, this distinction can be really important. If I'm going down to like 10 dimensions, or 20 dimensions, it's not so important, because with a larger dimension, I'm going to, okay, I essentially am giving up one of my dimensions in order to kind of, by going through I can pick 19 dimensions that go through the data, and then I can have another dimension that includes the origin. And so the difference between 19 and 20 for K is not going to be very big. But if I want to visualize this, it's important I use PCA and not SVD. So this is very important for Viz. Okay, and so the trick is to so basically I'm going to have 2 steps. First, I'm going to center data, and 2, I'm going to do the SVD plus, the top K. I'll take the top K. So this is what's called centering the data, and basically this centering is shifting so that the mean of the data. So this mean of the data, I move that to the origin. So I calculate the mean of each column. I can calculate the average value of each column and then subtract that off the column. So this is all I'm doing, and then I do the SVD, and so I recover, and that gives me the best subspace that is not restricted to go through the origin. And so to show that this works, we basically just show that this solution must always contain the mean of the data, and then you just shift the mean to the origin and you run SVD. Okay? So, so I can calculate this center vector, I'll call it C1, C2, up to CD, where Ci is going to be 1 over n of sum over I equals 1 of a, so let's call this j from 1 to n of ij, right? So I'm taking in the ith column, I'm going to take the jth. Maybe I got these backwards, but you're kind of taking. I have a here, and then this will be. This is a I star. Everything that's in this column, I take the average for all AI. I map to a tilde equals AI minus this. Well, let's call it a. Messing around with coordinates here, but I'm subtracting off for every. I'm creating this a tilde, which is a centered version, which is I'm taking the original row and I'm subtracting off this whole center vector here. And I subtract the same center vector for every row, and that's going to center the whole matrix. That'll move it so that the data is then going to be shifted onto the origin. Right? I'm shifting. This is basically subtracting off this center vector. Okay, and this low dimensions. Yep.
So you shift it onto that vector. Do you have to do any normalization onto that vector?
Yeah. So normalization will destroy your singular values. Right. If I do some normalization where I make it so all the vectors have the same, like are all, or they all have the same kind of, like on average they have they're normally distributed around the origin, something like that, I'm going to lose all the norm information about the data. And outliers will change what that does in strange ways. We'll talk more about this on Monday. Okay, so that's these are. What about normalization is an interesting question. It's often done here, and basically, if your coordinates don't match, that's often what people do. But it's kind of a hack, and it's not clear what it means after you do normalization. So it's an interesting question because it's often done, but there's no rationale for actually doing it that I understand. Okay, so I want to mention one more thing in the last 5 minutes. Eigen Vectors and Eigen Values, and we talked about this a little bit. Let's say I've got a square matrix V. Let's say it's an R M by M. Right then, if I can set up V times V equals lambda times V, where V is a vector in Rm, and lambda equals a scalar, then this is an eigenvector and eigenvalue. Okay, and so I mentioned in spectral clustering lecture that we could find these, and it's basically, we'll see it uses the same sort of backends which are written in Fortran. That's in all programming languages, from MATLAB to Python to C, that you can call. That's going to give you eigenvectors or eigenvalues based on the same stuff that does the SVD. There are various implementations, but if you call it like in MATLAB, it automatically figures out what's the right implementation to use. Up to sometimes you need to do stuff for sparsity, and we'll talk about that later. Okay, there's a little bit of flexibility here, so we usually restrict that the norm of V equals 1. Okay, so what are these eigenvalues and eigenvectors? So the way to think about it is I can create a matrix, a square matrix, VR, which is going to be A transpose A, and now these are going to be in R D by D. So if I took my input N by D matrix I talked about for PCA, and I did A transpose A, I'm going to get a D by D matrix VR. And similarly, I can create another matrix VL, which is A transpose, which is going to be an R N by N. Okay, so now I'm going to have that the eigenvectors of BR are going to be equal to the right singular vectors of A. And the eigenvectors of BL are going to be equal to the left singular vectors of A. And the eigenvalues of BR or BL are going to be equal to the squared singular values of A. Okay, so if I create the square matrix by doing A transpose A or A transpose, then I'm going to the eigenvectors of these square matrices are exactly the right or the left singular vectors of A. And if the let's see, if A is rank D, so it has D singular vectors, then BR is guaranteed to be what's called so it's what called so positive definite. A square matrix is positive definite if all of its eigenvalues are also positive. If all of its eigenvalues are positive or 0, then you say it's so then you say it's positives. So then it's called positive. So then it's called positives. So then it's called positive semi-definite if the eigenvalues might be 0. So so a square B is positive definite if all eigenvalues are greater than 0, and it's positive so semi-definite if the eigenvalues are greater or equal than 0. Okay, it's going to have n, or if it's m by m matrix, it's going to have m of these eigenvalues. If they're negative, it means that it's kind of a weird, you're probably doing the wrong thing by analyzing its eigenvalues and eigenvectors. At least if it's related to data. If these things come up in like some differential equation sort of work, and then maybe it makes sense. But if you're thinking about it from a data perspective, you're getting these square matrices either from the Laplacian or from taking a data matrix A and multiplying it by itself. That's usually where these things come up in this context. So this is roughly what you need to know about in this space. But they'll come up, Eigen Vectors, eigenvalues come up all over the place, and so now you kind of hopefully see a little bit of this relation. So on Monday, we'll talk about some metric learning, where this will include multidimensional scaling, which will be kind of another kind of cousin of all of these things, and some other ways of kind of how to choose a good distance among some data set, which has to do with what if all your coordinates, your columns don't have the same units. Yeah. Yeah, I'll try and post that soon. Let's say by the end of the week. Yeah. One center vector, which is equivalent to
How do you do in the
no, each one is bound. Yeah, so this is something of all elements. You can also do this on like the transpose.